Hey everybody, it's Mr. Mott. Thanks for coming back for the second video. Um, right now, we're going to pick up where we left off. As a reminder, on the left-hand side of the screen, we are looking at titrating the base with a strong acid. On the right-hand side of the screen, we are titrating a weak acid with our strong base. Something to kind of recognize on the left-hand side here is that we have 10 milliliters of our base, which is also 0.1 molar, and 10 milliliters of our acid, also 0.1 molar. So what that means, if our molarity and our volume is the same, the moles of NaOH, which is a strong base, and our moles of our strong acid are the same. And if you remember, as far as our reaction, we always think about a neutralization first. So here's our neutralization. And we are making NaCl. We don't have any more of our base or our acid left over because our moles are equal. So at equilibrium, we have 0 of these. We're making water, and then remember that sodium chloride, this is a neutral salt. And so that's not going to be interacting with water to change the pH. So what does that mean? It means our pH is equal to 7. Okay, nothing to really calculate there. We're just making water. On the right-hand side, we have again the same number of moles, but what we're making isn't a neutral salt. So let's go ahead and write all that out. Our moles for each of these are going to be the same. So we'll take our molarity, 0.1 molar, times our volume, 0.010 liters. And so that's going to be 0.001 moles. And that's moles of NaOH and moles of HCl, since the volume and the molarity is the same. Let's go ahead and write our reaction here. We've got NaOH reacting with our acetic acid. And that's going to be in equilibrium. We're going to be making our H3O plus. Oh, no, I'm sorry, not H3O plus. We're going to be making H2O, of course. So that's going to be making H2O. And then our, I guess we should write out the NaC2H3O2, our sodium acetate. So our moles, it's a little bit redundant, but our moles are the same. So we can write that out, and then we can see since our moles and our neutralization are the same, those are going to react, and we're not going to have any of those left over. One of the reasons I write this out is to really emphasize and not just skip over the fact that we are making our sodium acetate. We didn't have any to begin with, but when the base and the acid react, we are making our conjugate base. And so we have conjugate base now that is going to be interacting with water. And so what we need to think about and write out is the fact that our conjugate base is interacting with water, and so we're going to have an equilibrium that's set up. All right, and so when I write my conjugate base, I'm going to ignore the sodium ions because they're spectators. So I'm going to have my C2H3O2 minus, and it's going to be interacting with water. Because it's conjugate base, we're making hydroxide ions. And then we are going to have our C2H3O2, the conjugate acid, being made. All right. Now, when we think about what we have, as far as our ice table in terms of our concentration, we have 0.001 moles of acetic acid. Now, for molarity reasons, we need to think about this in terms of the total volume. We have from up top here 10 milliliters plus 10 milliliters, we have 20 milliliters or 0.02 liters. and that's going to help us with our concentration. All right. So we ignore water. We don't have any hydroxide or conjugate acid to begin with. Our change is going to be minus x plus x plus x. When we do this calculation here, 0.001 divided by 0.02, we should get 0.05. And so 0.05 for our molarity minus x, and then we have x and we have x. Now, we are going to ignore this change in x in our k expression here. We need to think about which k that we have. We are looking now at this. This is our conjugate base, so we actually need a kb. And so if you remember the relationship between, say, Ka and Kb, they multiply, and they're going to equal 1 times 10 to the minus 14. And so when we figure out what our Kb is, we're going to take 1 times 10 to the minus 14. We're going to divide that by our Ka, 1.8 times 10 to the minus 5. And when we do this math here, we get 5.56 times 10 to the minus 10. All right. Now, we're going to plug that into our expression, our K expression, and so that we can then figure out our X value. And so 5.56 times 10 to the minus 10 equals x squared over 0.05. And so again, we are going to be ignoring the change in x because our k value is very small. It's even smaller now as well. So when we solve for x, I'm coming up with 5.27 times 10 to the minus 6. Sorry, I squeezed that in there a little bit too tight. Okay. So 5.27 times 10 to the minus 6. That didn't work very well. All right. So move that over. All right. Now, we want to remember is that our X value is the hydroxide. So when we take the negative log of this value, we're getting our POH. All right, so let's see if I can fit that in up here. So for the POH, I'm getting the negative log of that value of 5.27 times 10 to the minus 6. The POH is equal to 5.28. All right. And if our POH is 5.28, we're going to subtract 14 minus that, and we get 8.72. And so that is our pH, and that's actually the pH at the equivalence point. Okay, so it took a while to kind of get there, but that's kind of the idea. And so if we compare and contrast our strong and stronger, pH is 7 because we made water and a neutral salt. For our strong base and a weak acid, our pH is around almost close to 9, 8.7, because we made a conjugate base in the reaction. All right. Next thing we need to look at is past the equivalence point, and that is going to be looking at when we have 12.5 milliliters of our 0.1 molar sodium hydroxide. And so our moles of NaOH, we can calculate that. 0.1 molar times our volume, 0.0125 moles. And so our moles of NaOH are going to be 0.00125 moles of NaOH. Our moles of acid from before, when we calculated it, be 0.001. So our moles of our HCl, 0.001. And let's go ahead and write down our neutralization here. So our NaOH, we had plus HCl, makes water, makes NaCl. Our NaOH, 0.00125, 0.0010 for our HCl. Those are our moles. The HCl is the smaller amount now, 0.001. It all reacts, and we're going to subtract our 0.001 here. And so we actually have some excess base in this case, so 0.00025 moles. All right, so we have some excess base here. Now, we can now figure out our concentration of hydroxide, and so we have 0.00025 moles. And now what we need to think about is that what's our total volume? We had 10 milliliters of HCl, and we have 12.5 milliliters of base that we added. So we actually had 22.5 milliliters, or 0.0225 liters. And so when we calculate this out, we get 0.011. And now from here, we're going to take that to figure out the pOH. So negative log of 0.011, and our pOH is going to be 1.96. So for our pH, we're going to take 14 minus 1.96, and we get 12.04. So we had our neutralization that happened. What we had left over was our strong base. That's the driving force in there, in that reaction. That strong base that's left over has a really big impact on the pH, and we're going to be at 12. Now, nice thing about being beyond the titration, even with the weak acid, you know, similar idea. We wouldn't have any of our weak acid or any acid left over at that point, whether it's strong or weak. And so we just have excess base, just like we did. And so your pH at this point for your weak acid is going to be the same. So guess what? It's going to be the same at 12. And if you have, if you remember in our lab that we've done, when we compared and contrast our titration curves for strong and weak, strong started out more like this, pretty flat, went up here, and ended around 12. So this was in blue, would be kind of the shape of the strong. And then for weak, pH was starting a little bit higher, kind of gradually increased a bit more. Your equivalence point was higher like we saw. Whoops. Your equivalence point was higher like we saw. But it finished out at that same pH, and that was at weak. But they were both right at the same, right around 12. Even though like your equivalence points for green would be here, and then for your equivalence point for blue be much lower for the strong. All right. Thanks for hanging in there. I know the videos are long, but hopefully they're helpful.